So I have the pleasure to introduce today's junior talk. So the speaker will be Felipe Garrido. So Felipe graduated from the Universidad de Chile in mathematics, and then obtained an excellence grant from PGMO to continue with a master in Paris. We got very lucky to have him coming to France. And he is now currently preparing a PhD at University Paris-Dauphine in the department LAMSAD under the supervision of Frida Laraki. So today's talk, he will speak about stable matching games.
Thank you so much, Xavier, for the nice introduction. So as he said, my talk is called Stable Matching Games, and it is my PhD thesis with my advisor, Frida Laraki. So I start. In the literature of stable matching problems, there are many articles. The first of them probably being the one of Gale and Shapley, who defined the stable marriage problem, in which two sets of agents, M and W, each agent having a strict preference ordering over the agents at the other side of the market, has to be matched in a stable way. What it means, what it is a matching, simply as an assignation mu, as we saw in the see in the picture. And this matching, it is stable if there is no one agent at one side of the market and there is no another agent at the other side of the market that they mutually prefer each other instead of the partner they have in mu. So some years later, Shapley and Shubik extended the problem to the housing market, in which now we have a set of buyers and a set of sellers. The agents, they trade indivisible goods. So simultaneously, they match and they define a monetary transfer to make from buyers to sellers. Later, Gale and Dimanche extended this problem by allowing monetary transfer from both sides of the market. These articles, they prove the existence of stable allocations, and they do it by using the Ferret-Acceptance algorithms. And well, they have proved many properties over the set of stable allocations gamma, and in particular that it is a lattice. So real-life interactions are much more complex than just some monetary transfer. For example, we're trying to find a job, or we're trying to get enrolled in a university. Besides the salary and some bonus or the scholarship and some tuition, we would like also to talk about flexible work hours or some projects that I may work. In the case of the university, some exchange that I may do during my time at the university, or some teaching experience that I may have. So our model tries to capture this idea of interactions that they are more complex and extends further the previous works. And for that, we will replace the monetary transfer by strategic choices in a two-player game. So I pass to explain our model. A matching game setting, or a matching game, is any setting in which we have two sets of agents, M and W, men and women if you prefer, such that for each potential couple, we will have a two-person game G. So now the agents will be endowed with strategy sets and payoff functions. In this setting, an allocation, or also called a matching profile, I will use both names, is any triplet pi consisting in mu an assignation between the agents, X and strategy profile for all the agents in M, and Y and strategy profile for all the agents in W. Given one of these allocations, we can compute players' utilities as simple the payoff that each agent obtains in the game that he's playing against the partner. So the utility of player I is the payoff that he obtains against the partner mu I when they play some strategies. Of course, that is the case if the player has a partner. If the player is single, he will receive his individually rational payoff, that is the personal valuation that they have for being single. Naturally, we are faced with two notions of stability. The first one is the one of Gale and Shapley, and is related to the relationship across couples. This one we pass to call it external stability. The second one is because of the presence of games, so we have the idea of Nash equilibrium. This is a notion that we will call internal stability. I will present you two solution concepts, so two ways of computing or two ways of defining allocations that are internally and externally stable. And we will see, we will compare both, and we will see which one is the best for our setting. So I pass to define the first one. The first solution concept is Nash stability. Given a matching profile pi, given an allocation pi, we say that pi is internally Nash stable if for any couple in mu, the strategy profile that they are playing is a Nash equilibrium. Pi will be externally Nash stable if, first of all, everyone gets at least their individual irrational payoff. So basically, nobody wants to break the couple and become single. And the second one is there are no blocking pairs, as in Gale and Shapley. In our setting, what it means that there are no blocking pairs, it means that there is no pair of agents, one at each side of the market, not matched by mu. And there is no Nash equilibrium for them, such that if they match and they play this Nash equilibrium, both of them increase strictly their payoff with respect to ones they have in the location. If pi is internally and externally Nash stable, we will call it simply Nash stable. We have existence of this kind of allocation, and indeed, if all the set of Nash equilibria are non-empty and compact, then we have existence of Nash stable allocations. The proof follows two steps. So first, we use the Ferrer acceptance algorithm for computing an epsilon approximation of this kind of allocations, and then we use the compactness for taking epsilon to 0. We will not see this proof in detail. Instead of that, I want to show you an example.
I have a quick question.
Yes.
Can you go back to the last slide? So why do you assume that it should not be in mu? IJ not in mu? I could imagine that there's a Pareto superior Nash equilibrium within mu.
Sorry, I didn't really get the question.
Why do you assume that IJ is not matched currently? Understand that this is the traditional way of looking at it. If you don't have Nash equilibrium play, but within the play, you might also allow it to also be in mu and a different Nash equilibrium.
Yeah, for sure. I mean, it's because external stability is related to it comes from the idea of Gale and Shapley. So it's basically you want to change your couple. The way that you want to deviate is by changing your partner. That's why you have to consider couples that they are not in mu. But this one is related to couples that they are in the couples in mu, the matched couples. So I don't know if that answers your question.
No, it doesn't. You're just saying why they do it. I just don't understand why you do it. No, that's fine. We can ask later. Don't worry.
We will continue. We will see. Maybe I answered your question during the rest of the talk.
May I ask a question too?
Sure.
It seems that when you talk about external stability,
yes,
you can say it's kind of a too strong Nash, because you allow a couple to do something which would benefit them both. So if you define the game to be if you augment the actions to allow them to deviate, then it's a strong Nash in a way. Well, when you talk about the actions of deviating, but when you talk about an equilibrium within the couple, then it seems like then you don't talk about strong Nash. Doesn't it make more sense to restrict yourself to strong Nash equilibria within when you talk about the internal stability?
Maybe, but indeed, the reason of defining this solution concept is because of the example that we have now. Even with this definition that is weaker than the one that you're saying, we are restricting too much the problem. So what I want to show you now is that this solution concept is not the good one, and therefore I will pass to the second one. So let me explain the example, and maybe this will answer to you.
Continue one more request, but maybe that's better for the questions after the talk. But basically, when you move to strong Nash, you on the one hand restrict what you look at. On the other hand, you make it easier because the other options also shrink. But okay, let's see
how it goes, and then we come back to the question. Sure.
Okay.
So with this example, I will show you that indeed this solution concept is too restrictive. So basically, consider a simple game with only one man and one woman. Both of them with the same individual irrational payoff, delta, some positive fixed value. If they match, they will play a transfer game. So given X, the transfer of the man, and given Y, the transfer of the woman, the man will obtain 10 times delta minus his transfer plus the transfer of the woman, and the woman will obtain the transfer of the man minus her transfer. We see, we see that the man is willing to pay anything, any transfer up to 9 delta to match with the woman, because in this case he's better off than being single. While the woman accepts to be matched, only she receives a transfer equal or higher to delta, so she's also better off than being single. The intuitive solution to this problem should be that the players should match, the man should make a transfer x equal delta, and the woman doesn't make any transfer. Under this solution, notice that both of them are better off than being single, and indeed, or weakly better off than being single, and indeed, this is the highest payoff that the man can obtain matching with the woman. However, if we come back to the Nash stability, internal Nash stability forces the players to play a Nash equilibrium. And the only Nash equilibrium in this game is to play zero transfers, because any positive transfer is a dominated strategy. And therefore, the only Nash stable solution, the solution that is both externally and internally, is to remain single, because without transfer, the woman gets a payoff of zero, and she prefers to play the couple and become single. So therefore, Nash stability is indeed too restrictive, because, for example, for this example, the players, they do not match and they do not trade anything. That's why we consider our second solution concept, that is only called stability, and I hope they will answer the idea of strong Nash or weak Nash that you asked before. A matching profile pi will be called only externally stable, so we forget the Nash, if, first of all, everyone gets at least their individual rational payoff, so basically nobody wants to deviate, so nobody wants to become single, sorry. And second, there are no blocking pairs. Indeed, in this case, if there are not blocking pairs, it means that there cannot be a couple, again, not matched between them. And there cannot be any strategy profile for them. Before we had here Nash equilibrium, now we have any strategy profile, such that if the players match and they play this strategy profile, they increase both strictly their payoff. If we recall the example, the previous example, notice that any solution in which the players match, the man makes any transfer in this interval and the woman doesn't make any transfer, it is an externally stable solution. And indeed, this coincides with the set of solutions of Gale-Shapley, Shapley-Shubik, and Gale-Dimanche models, the model that I mentioned at the beginning. So we obtain in particular a continuum of solutions. Now, what about internal stability? Before, we were forcing the players to play Nash equilibrium. Now, we will allow them to somehow play dominated strategies. So, informally, I will give the formal definition later. A matching profile, an allocation pi that is already externally stable, will be also internally stable if for any couple, either they play a Nash equilibrium, so no agent has a profitable deviation, or any profitable deviation breaks external stability. What it means? Now, players, if they want, they can play dominated strategies, but they do it because if they deviate, the partner will prefer to leave the couple. So players will be allowed to play dominated strategies in order of preserving the partner. If we recall again the previous example, we find that the unique externally and internally stable solution is the intuitive one that we found before. So the players match, the man makes any transfer, makes a transfer x equal delta, and the woman doesn't make any transfer. Notice that if the man decreased by epsilon his transfer, so he increased, that's a profitable deviation for him, the woman prefers to play the couple because she's better off being single. So indeed, the man makes a dominated strategy in order of keeping the partner. Internal stability, this notion is our novelty, and as we saw, it refines the literal solutions. So this is the model that I will consider, and now I can show you the existence of this kind of externally stable allocations. So basically, if for any matching game in which we have compact strategy sets, a continuous payoff functions, we can always find an externally stable matching profile. It always exists. The proof follows two steps. The first one, it uses an extension of the deferred acceptance algorithm of Gale-Dimanche and Sotomayor. We use it for finding an epsilon approximation of this kind of strategy profile, and then we use the compactness and continuity for taking epsilon to 0. So we obtain existence of this kind of allocations. we can work now with the set of this kind of allocations. So the set of externally stable matching profiles gamma is a semilattice. It means that what it is a semilattice, it means that we can only define the maximum between two elements, but not the minimum. The minimum is not well defined, unless all the games are strictly competitive. If players are playing strictly competitive games, the minimum between two elements is well defined, and even more, we obtain the duality between the maximum with respect to one side and the minimum with respect to the other side of the market. So indeed, gamma becomes a full lattice as in Gale and Shadow. Finally, one last property is that our algorithm outputs the highest element in the lattice with respect to the proposer side, exactly as Gale and Shadow. So now I can pass to explain you properly, or define you properly the internal stability, and for that we need the new concept of constrained Nash equilibrium. Given any couple ij, potential couple, we will endow them with outside options, some real values. A contract or a strategic profile xy will be feasible for this couple for these outside options if both agents obtain at least these values when they play this contract. And we have probably now the most important definition of the talk. A contract x prime y prime that is feasible will be a constrained Nash equilibrium if, for any other contract, if one of the agents is better off, the partner gets a payoff that is lower than his outside option. So we can see this as it follows. We have agents at the two sides of the markets, and agents are proposing contract between them. So I'm proposing something X, you're proposing something Y in exchange. And if in some moment the contract XY that we are proposing between the two of us, we like it, we match, and we play this contract in our game. A constrained Nash equilibrium, it is one of these contracts such that for any other contract you may offer me in which you are better off, I will not accept it indeed because my payoff goes below my outside option. And for sure, I want to obtain this outside option as a minimum payoff. So with this in mind, we have that constrained Nash equilibria indeed capture the idea of internal stability. Why? Because if the outside option that we consider are the lowest payoff that I'm willing to obtain for being matched with you, if you make a profitable deviation and my payoff goes below this minimum payoff, I will leave the couple and I will try to propose to someone else. Another way of seeing constrained Nash equilibria is the following. They are Nash equilibria indeed, but subject to a participation constraint. So indeed, constrained Nash equilibria are best reply between with respect to the strategy of the partner, such that both players are obtaining at least their outside option. So they are best reply subject to some feasibility constraint. This kind of equilibria do not always exist. We cannot guarantee the existence. So we will consider a new class of games, the class of games, the class of games called feasible games, in which a game definition, a two-person game G will be called feasible if for any pair of outside option which admits at least one feasible contract, there is also one constrained Nash equilibrium. And this class of games is also our novelty, and it's a necessary condition for having internal stable allocations. And we have proved that there are many well-known games in this class indeed. So all the zero-sum games, strictly competitive games, potential games, and infinitely repeated games, all of them are feasible. But not all the games will be feasible. And indeed, I want to thank our speaker of today for this counter example, considering this bimetric game in mixed strategies, and considering outside options equal to 0, it's impossible to compute a constrained Nash equilibrium, even if there are many feasible contracts for both players. So this game is not feasible. Finally, I explain you how to compute the allocations that are externally and internally stable. And for that, we have an algorithm. So as an input, consider any matching profile, pi. And we do the following. Consider a couple, any couple, it doesn't matter which one, and compute their outside options. Once computed the outside options, we check if the strategy profile that they are playing is or is not a constrained Nash equilibrium. If it is not, we will compute one using the fact that the game will be feasible and having an oracle for the game. Then, having the constraint Nash equilibrium, we replace the strategy profile that the players are playing by this equilibrium. Then we pass to do the same with the second couple, the third couple, we compute all set options, and we start to change all the constraint Nash equilibrium until the last couple. Once we have finished with the last couple, we have to come back to the first one, because when we change the strategy profiles, we change the payoff of the players, and therefore we change the outset options. So maybe the constraint Nash equilibrium that we considered for the first one is not a constraint Nash equilibrium anymore at the end of the procedure. So we need to come back and we need to do it again, and we repeat this procedure until convergence. One important property is that this procedure doesn't affect the external stability. So if the input is externally stable, the output is also externally stable. Therefore, we obtain the following theorem. If the algorithm converges, it outputs an external and internally stable matching profile for any setting with feasible games. Even more, we know that the algorithm converges in all the feasible games previously mentioned. So for zero-sum games, strictly competitive games, potential games, and infinitely repeated games, the algorithm converges. Conclusions of this talk. We have generalized Gale-Shapley, Shapley-Shubik, and Gale-Dimanche models. Our external stability notion corresponds to the pairwise stability. We have proved in a constructive way the existence of externally stable allocations. The model of Gale-Dimanche, the one of matching with transfer, is a particular case of ours when players are playing strictly competitive games. And so we generalize the results, including the lattice structure. We have introduced internal stability. This is our novelty. That is a Nash equilibrium notion subject to participation constraint. We introduced also the class of feasible games, and we have designed an algorithm for computing internally stable allocations. We have proved that the class of feasible games includes potential games, zero-sum games, the competitive games, and infinitely repeated games, all of them. And one final remark, there is another important model in the literature, that is the one of matching with contracts of Hatfield and Milgrom. Our notion of internal stability is also a refinement of this model, but this refinement depends on how the game interaction between the partners is modeled. For example, different bargaining games lead to different surplus sharing. Finally, as future extensions, we have in mind the one-to-many and the many-to-many model. We have to study the complexity of our algorithms and the computation of a zero-stable allocation. That is still an open question in the literature of stable matching games, or stable matching problems. Sorry. And finally, to find some good applications for this model. The articles of today, and thank you so much.
Okay, so thanks, Felipe. We have time for one or two short questions. There were already some questions during the talk.
Yeah, for sure. Now we can come back to the question that people made.
Well, I was worried about the, I'm now worried about the matching. Once we're in the matching, it's as if you see my strategy, because if you allowed me to do anything, then I would play the dominant strategy and we would require Nash equilibrium. So how is the story that you require, that you would like to tell us? I never heard a story, it was just mathematics. So can you tell me, once we're matched, how do you explain the story of us playing the game?
So the game is played in simultaneously to when you choose your couple. So the story is basically is like this two group of people trying to propose contract between each other.
So I'll set x equals 0. I will ignore your constraints that it has to be feasible relative to the outside and just set x equals 0 in your counterexample. Who will prevent me from doing it?
I mean, if you propose something that I don't like, I will not match with you.
No, but you don't know. I'm not going to propose it. We're not proposing. We're matching. I might propose that I have x equals delta, but then when we play, actually, I'll play x equals 0. That's my problem with this. There's not a proposal. That's why I'm trying to understand the intuition that you have when you and me meet. I can propose delta, but I won't play delta, and you cannot punish me.
Yeah, but then I can be with someone else, and I can propose to someone else.
No, but you don't do someone else because you like me, because it's a stable matching, and you're externally and internally stable.
No, because if you propose me something, and then we match, and you play something else, the final result is not going to be stable.
Oh, so you're thinking about something dynamic. So that's what I want to know. So it's basically something dynamic. So
there's a different model in which we have like a two-level game. So first we match and then we play. That will be another model. Here's everything simultaneous. So basically, you define something, and then if at the end of the day you cheat and you do something else, well, the solution will not be stable. So I will have somebody else that I would like to propose, or maybe I would prefer to become single. So
that
we
helps.
play
Thank you.
the standard. Okay, thank you.
Okay, so I think we should, since there was some question, we should take the break now, not get too much late. Thanks again, Felipe, for the presentation.
Thank you so much.
So we take a 5-minute recess and then we start with the presentation of Elon.